Every nerve in his body was on fire, a mix of adrenaline training pure, unadulterated focus. This was the moment, the culmination of thousands of hours of practice. He ran through his final checks one last time. It was muscle memory now, a fluid dance of fingers across switches, buttons, flaps set, engines spooled up to a deafening roar, systems green across the board. The deck crew, a blur of colored jerseys, gave him the final thumbs up. He returned the gesture, a crisp salute that said, "I am ready." The jet blast deflector, a massive steel wall, was raised behind him, protecting the crew and aircraft further back from the inferno shooting out of his engines. He was now connected to the carrier itself, linked to the very heart of the ship's power. He was no longer just a pilot in a plane, he was the tip of a spear about to be thrown. The final signal came, then shot his hand forward, pointing down the runway. That was it, the signal to unleash hell. So why all that drama? Why the need for such an extreme launch system? It all comes down to a fundamental problem of physics. Let us break it down. Your average fighter jet, like the FA-18 Super Hornet, is a heavy piece of machinery. When fully loaded with fuel and weapons, it can weigh over 60,000 pounds. That is the weight of about 10 large pickup trucks. To get something that heavy to fly, you need to achieve a critical speed, called takeoff speed. For a jet like this, that is somewhere around 150 miles per hour to 170 miles per hour. It needs that speed for its wings to generate enough lift to overcome gravity and actually fly. Now think about a normal airport runway. They are long. A typical commercial runway can be 2 miles long or even more. This gives a heavy plane plenty of room to fire up its engines, gradually accelerate, and build up the necessary speed to lift off the ground gracefully. But an aircraft carrier does not have that luxury. It is a floating city, sure, but it is not a floating continent. The flight deck of even the largest supercarrier, like the USS Gerald R. Ford, is only about 1,100 feet long. And the actual runway, the part used for launching, is much shorter than that, only about 300 feet. That is shorter than a single football field. Trying to get a 60,000-pound jet to 170 miles per hour in just 300 feet using only its own engines is, to put it simply, impossible. It is a non-starter. They would just trundle down the short deck and unceremoniously drop into the ocean. It would be a very short, very expensive, and very wet flight. For over half a century, the answer to this problem was steam. Pure, raw, high-pressure steam. It sounds almost archaic, but steam catapults are an incredible feat of engineering. Imagine a giant, superheated water boiler deep within the ship. This system takes seawater, desalinates it, then heats it under immense pressure to create superheated steam. Not the steam from your kettle. This is high-energy gas. It is the muscle behind the entire operation. Steam is held in accumulators, giant pressure cookers waiting to be unleashed. The catapult is basically a very, very long pair of pistons inside 2 parallel cylinders running under the flight deck along the launch track. These cylinders can be over 300 feet long. On deck, you see a small metal block called a shuttle. The shuttle connects through a narrow slot down to the pistons below. Before launch, the jet's nose gear is attached to the shuttle by a launch bar. The jet is now physically connected to the pistons. A holdback bar keeps the jet from moving while the engines spool up, building tension like a drawn bowstring. When the launch officer signals, it is showtime. Massive valves slam open, some weigh several tons. Steam is released from the accumulators and blasted into the back of the cylinders. The sudden explosive expansion is like a bomb going off. It slams into the pistons with unimaginable force. Steam catapults are powerful and have served navies well for decades, but they are complex, mechanically intensive, and have their limits. They are, in many ways, a brute force solution. Enter the next giant leap in launch technology, the Electromagnetic Aircraft Launch System, or EMALS. This system does away with the steam, the pistons, the valves, and the complex plumbing. Instead, it uses the clean, controllable, and incredibly powerful force of electromagnetism. If the steam catapult is a giant steam-powered hammer, EMALS is a high-tech railgun. It represents a fundamental shift from mechanical to electrical engineering. At the heart of EMALS is a linear induction motor. Now, that sounds complicated, but the principle is something you might already be familiar with. Think about a modern roller coaster launch. rock and roller coaster at Disney World, launching you from 0 to 60 in seconds without a chain lift. It uses powerful magnets. Emails is a much more powerful version of that same idea. The system consists of stator coils, powerful electromagnets, arranged along the catapult track just under the flight deck. The shuttle the aircraft connects to has a large aluminum plate attached. At launch, a huge amount of electrical energy is drawn from the ship as power grid. New carriers like the USS Gerald R. Ford are equipped with nuclear reactors. So, we have two different technologies that do the same job, flinging jets off a boat. But how do they really stack up? Let us compare steam and emails. Think of the steam catapult as a sledgehammer, incredibly powerful but not very subtle. One setting, hit it as hard as you can. Massive sudden strain on the jet is airframe. Every launch is violent, wear and tear. Jets need more maintenance and have shorter service lives. Steam systems are very heavy. They take up a lot of space. They require huge amounts of fresh water, precious on a ship. Emails is like a surgeon's scalpel, controlled by software, force tuned with precision. It knows the aircraft's exact weight. It calculates the smoothest acceleration profile, gentler but equally fast launches, less stress on the frame, longer aircraft life, fewer repairs, huge savings for multi-million-dollar planes. Emails has a wider operational range. Steam struggles with very light aircraft, like unmanned drones. Steam's minimum power is too high, like tapping a thumbtack with a sledgehammer. Emails dials way down for drones, dials way up for heavy, fully loaded fighters. This flexibility is critical for a mixed manned-unmanned future. Emails is more efficient, lighter, requires less maintenance, and needs fewer operators. Let us walk through the launch sequence step by step. It is a ballet of precision and power that happens in the blink of an eye. You know, it all starts long before the pilot even gets to the catapult. The aircraft is taxied from its parking spot to the launch area. A flight deck crew member, known as a director, guides the pilot using hand signals. Once in position, the pilot lowers the launch bar on the jet is nose gear. A crew member then connects this bar to the catapult is shuttle, sitting flush with the deck. At the same time, the holdback bar is attached to the rear of the aircraft. The jet is now physically tethered to the ship. With the jet locked in, the pilot and the deck crew run through their final checks. The pilot pushes the throttles to full military power, and if needed, engages the afterburners. The engines howl, and a wall of superheated gas erupts from the back, deflected safely upwards by the jet blast deflector. The entire aircraft strains against the holdback bar, designed to withstand tens of thousands of pounds of thrust. The pilot gives a final salute to the catapult officer or shooter, indicating they are ready. The shooter performs a final visual check of the aircraft and the deck, ensuring everything is clear. The shooter then gives the iconic launch signal. On a steam catapult carrier, they would touch the deck and sweep their arm forward. With emails, it is often the push of a button from a control station. The instant the signal is given, the catapult fires. If it is steam, the valves open. If it is emails, the magnetic field is generated. The holdback bar breaks, and the shuttle rockets forward, dragging the 30-ton aircraft with it. The acceleration is mind-boggling. In just over 2 seconds, the jet goes from a complete standstill to nearly 170 miles per hour. The pilot is a passenger at this point, their hands off the controls, simply holding on. As the jet clears the end of the flight deck, the launch bar automatically disengages from the shuttle. What is it actually like for the human being sitting in the cockpit during this violent event? In a word, brutal. During a catapult launch, a pilot experiences extreme G-forces. G stands for gravity, so 1G is the normal force of gravity you feel every day. During a launch, a pilot is subjected to around 4 Gs. This means they feel a force equal to 4 times their own body weight, pushing them back into their seat. If a pilot weighs 180 pounds, it feels like a 720-pound weight is crushing them into their chair. It is a sudden, immense, and sustained pressure. This intense acceleration has profound effects on the body. The first thing that happens is that all the blood in your body wants to rush to the back of you. Your eyeballs are slightly compressed in their sockets, which can momentarily distort your vision. It becomes extremely difficult to move your arms and head. They feel incredibly heavy. This is why pilots are trained to keep their head pressed firmly back against the headrest and their hands in a specific position. Trying to reach for a switch during launch would be almost impossible. Breathing also becomes difficult, as the G-forces compress your chest and diaphragm. To withstand these forces, pilots undergo extensive and rigorous training. They spend time in centrifuges, which are machines that spin them around at high speed to simulate G-forces. This helps them learn breathing techniques, like the Hick maneuver, which involves tensing muscles, and controlling your breathing to keep blood from draining from your brain, which could cause you to black out. They also need to be in peak physical condition. The strain on the cardiovascular system and muscles is significant, and only a healthy body can consistently endure it without injury. It is not just about knowing how to fly the plane, it is about having a body that can survive the ride. Despite the intensity, for a trained naval aviator, the catapult launch becomes routine. They describe it as a swift kick in the pants that gets their attention, but it is the price of admission to their office in the sky. So, we have explored the incredible science and raw power behind launching a jet from a carrier. It is a fascinating piece of engineering, a real-life David versus Goliath story of physics. But why go to all this trouble? Why build these billion-dollar catapults on these multi-billion-dollar ships? The answer is simple and profoundly important for global security: reach. An aircraft carrier is fundamentally a mobile piece of sovereign territory. It allows a nation's military to project its air power anywhere in the world without needing permission from another country to use their airfields. Think about it. In a crisis, political situations can be messy. A friendly nation might be hesitant to allow foreign fighter jets to operate from its soil. With an aircraft carrier, that problem vanishes. The ocean is international territory. A carrier strike group can sail to a hotspot and establish a powerful presence just over the horizon. Destroyers, cruisers, submarines. The carrier is air wing, enabled by catapults and arresting gear, can conduct missions for defense, deterrence, humanitarian aid. It provides a flexible, powerful tool for diplomacy and defense. This capability acts as a major deterrent. The presence of an aircraft carrier sends a clear, unambiguous message. It demonstrates commitment and the capability to back that commitment with serious force. The thunderous roar of a jet being flung off a flight deck is not just tech, it is the sound of a nation projecting influence, protecting interests, maintaining security.